Okay, this is the Bohr model of the atom. We're going to talk about Niels Bohr and his contribution to the modern atomic theory. A quick thank you to Zhiquan Zhu for drawing the pictures of the scientists. If you remember, in 1909, Ernest Rutherford conducts the gold foil experiment and discovers that the atom is mostly empty space and that the atom has a nucleus. Now, the gold foil experiment was where he shot alpha particles at a very thin sheet of gold foil, saw most of the particles went right through, a very small percentage deflected, and he came up with a model of the atom that had a positive charge at the center called the nucleus with electrons on the outside of the atom. So, this is the Rutherford model of the atom. There is a problem with this model of the atom. And the problem is that according to classical physics, the electron should be falling into the nucleus and releasing energy in the form of light as it does so. So as it continually falls into the nucleus, it should be continuously and constantly releasing energy. So you can see here the path of the electron as it spirals into the electron spirals into the nucleus and the energy that's being released off in this picture. In short, what this means is the atom shouldn't exist. Using Rutherford's model of the atom should not exist because the electrons would fall into the nucleus. So we have to come up with a way to explain what's going on. And that's where Niels Bohr comes in. Niels Bohr noticed that when you looked at light from an incandescent bulb, it created an entire rainbow spectrum of light. So when the light goes through a prism, there's an entire rainbow spectrum, which are the different wavelengths of light, which correspond to different amounts of energy. Different wavelengths give off different colors of light, which correspond to different amounts of energy. Red being really low energy, and blue, violet being really high energy, visible light. So you look at the spectrum and you can see a complete rainbow. He also noticed that if you look at different elements and isolate elements, and you put them in tubes and you pass an electrical charge through them, they glow different colors. You don't see white light that can be divided into the rainbow spectrum. What you see are very specific lines, as you can see here in the hydrogen spectrum. Hydrogen is a pink gas, and you see very, very specific lines called emission spectral lines from hydrogen. So he began to think, well, why is this? Why does a light bulb give me the entire rainbow spectrum, whereas hydrogen only gives me these four lines: red, teal or bluish green, blue, and violet? Okay, so why is this happening? And if you start to look at other emission spectra of different elements, what you notice is that each element has its own unique emission spectra. You can see here that we have hydrogen, helium, and neon, and they're all different colors, and they all have different emission spectra. We have the emission spectra from the light bulb, we have the emission spectra from hydrogen, we have the emission spectra from helium, and we have the emission spectra from neon. Okay, and they're all different. Okay, so what Niels Bohr does in 1913 is he offers an explanation for why this is. And this is going to be the really important aspect. It's going to give us not only an explanation for the emission spectrum, but it's also going to create a new field called quantum mechanics. And this is his model of the atom. So the Bohr model of the atom states that an electron exists in distinct energy levels. The atom absorbs energy, and the electron jumps to a higher energy level. So you can see here the electron jump to a higher energy level. The atom then releases the energy in the form of light, and the electron will return to the ground state. And each atom has different amounts of energies between the different energy levels. So the color of light that is produced is dependent on the amount of energy released. So that's why the different elements produce different emission spectra. So for hydrogen, if you take a look at a hydrogen atom, he said that all atoms have 7 energy levels. If you take a look at a hydrogen atom, we saw a red, a teal, a blue, and a violet line. Well, the red line came from the electron dropping from the third energy level to the second energy level. The teal line comes from going from the fourth to the second. The blue line comes from the fifth to the second, and the violet line comes from the sixth. Comes from dropping from the sixth to the second energy level. The amount of energy that's released is dependent on the distance the electron falls within the atom. Okay, how many energy levels it goes down. As the electron gets further away from the nucleus, its energy increases. As it comes closer into the nucleus, it decreases. So you can see how these different colors correspond to the different amounts of energy. A way to think about this would be if you stood on a chair and you jumped off and you hit the ground, you'd make a certain sound. If you stood on top of a desk, you'd make a slightly different sound. If you stood on top of a building and jumped off, you'd make a different sound. The sound that you hit, the sound that is made when you hit, corresponds to the amount of energy that is being transferred as you jump off the object. So, within the atom, the amount of energy absorbed when an electron jumps to a higher energy level and released when the electron falls to a lower energy level is specific. The term is quantized, which is where we get quantum mechanics from. And this explains why only certain colors are seen, and certain colors are seen in the emission spectra, and every atom has a unique emission spectrum. Bohr basically has put the electron into stable orbits around the nucleus, but these orbits are actually energy levels. And we now have what is known as the quantum atom. So what Bohr does is he creates an atom where the electrons exist in energy levels that are quantized, and thus starting us down the road of quantum mechanics.